Welcome to second episode of System Design Series. In today's episode, we'll be tackling designing hotel reservation system from the scratch. A big disclaimer, before we start, most of the design today is derived from or inspired from Alex Zhu's system design book. I saw a bunch of system designs for hotel reservation system. By far, Alex Zhu's explanation made the most sense to me, and this was the design I liked the most. In today's episode, I'll be adding my own twist, but I highly recommend buying Alex Zhu's work and checking it out. Recently, I was listening to Stephen Bartlett's podcast. He talks about 5 buckets. Knowledge and skill are the top 2 buckets. He says you fill the skill bucket by applying the knowledge you have learned. And I find that applying the knowledge is way more effective way to learn something. By sharing this video, I have definitely developed a deeper understanding of the concepts. I hope this video will be helpful to you in one way or the other. Let's start with the very first step, which is gathering functional requirements. So we are building system design for hotel reservation system. And the first step is gathering functional requirements. At this point, we need to clarify what kind of reservation system we are building. Are we building a reservation system for a boutique hotel, or are we building a reservation system for a national chain of hotels like Hilton? Or are we building a reservation system for Airbnb? I think the most interesting part where we can employ a lot of system design strategy is building a reservation system for a hotel chain. So we're going to go ahead and design a system which lets us reserve hotels. The first functional requirement is user should be able to make a reservation. We have all reserved a hotel at some point or the other, so we know what the experience is. So this is one of the problems where we don't need a lot of domain knowledge. We have a fair understanding of what to expect, but it is good to always clarify that with your interviewer if you are solving this problem in an interview setting. Okay, so user should be able to make a reservation, and user should be able to retrieve a reservation. User should be able to update a reservation, and user should be able to cancel a reservation. So we are going to assume that we are going to build this reservation system for a hotel chain, and this hotel chain has about 1,000 hotels, and each hotel has about 500 rooms, max of 500 rooms. I think this is a big enough system that we can employ a lot of interesting strategies. We clarified that we want the user to be able to do CRUD operations on a reservation. Along with these requirements, we also have a requirement where user can browse a list of hotels in a geographical area. Say for example, the user wants to see all the hotels in the state of California, and user should be able to click on a specific hotel and get more details about that hotel. Let's write that down. User should be able to see list of hotels in a area. User should be able to see specific details of a hotel. Example, what kind of rooms are available, pricing, etc. I think this is a pretty good summary of functional requirements. When we are working on functional requirements, we want to gather as much context as possible so that it will naturally lead us to the next section. API design and data modeling. So before we go ahead into API design and data modeling, let's take a few seconds to think about the characteristics of the system. We know that hotel reservation system is more read heavy than write. Why? Because majority of the people who go to the reservation page don't end up making a reservation. So the system is more read heavy than write heavy. And also when we are making a reservation, we want it to be consistent. So we want the ACID properties of a database. So we don't want to be eventually consistent. We want to be highly consistent. For all these reasons, we're going to pick a relational database system. So choice of database technology here, RDBMS. So the next step is identifying entities and defining REST APIs. So why did I go with REST APIs here? Because the cadence of messages produced or consumed is not very high. So a client server model is perfectly acceptable in this design. So the next step is identifying resources or entities. So from the functional requirements, we can identify user entity, reservation entity, hotel entity, and room entity. So now that we have identified the resources, I'm going to define CRUD APIs for all of them. I'm going to skip the user one because that is not the one that is in focus for the hotel reservation system. We are going to define REST APIs for the hotel resource. We want an API to create a hotel. So this API will be used by staff. It would be HTTP post. URL path would be something similar to this one. And the input request body would contain all the details about that hotel. And the response would be a hotel resource ID. It could be something like this. For example. And we need an API to get details of a specific hotel. So get that would be HTTP get. The URL path would be hotel ID, and the response would contain all the details of the hotel. We'll come back and define these details later if needed, but we are going to skip those at this point. So this get details of a hotel returns details of a specific hotel. We also need an API to list all the hotels in the geographical area. So list hotels. This would also be HTTP get. This is what the URL path would look like, and the response would be a JSON array of hotels. We can define a hotel info object which would contain all the details of the hotel along with a URL link for S3 or a blob storage where we can pull image of the hotel, but we are going to gloss over for now. We also want an update API, update specific hotel. That would be HTTP put because we are updating a resource, and hotels, hotel ID, and this would be the URL path, and the request object would contain the request object would contain fields that would need updating. The and the output can contain the hotel object, which is the same response you get from get details of the hotel API. Okay, and delete a hotel. This would be HTTP delete, and the URL path would look something like this. So while listing these APIs, see that there are two personas. One of them is the guest persona, where a customer is using the hotel, and the other one is the hotel staff. So we are designing the system primarily for guests of the hotel. Now we are going to design REST APIs for room resource. We want the hotel staff to be able to create a room. This would be HTTP post. The URL path would be v1 hotels, hotel ID, rooms. So we have a hierarchical relationship between hotel and rooms. So a hotel can contain many rooms. So it is natural for the hotel identifier to come first in the URL, and later we can follow with the room identifier. So here we have v1 hotels, hotel ID identifier, and then rooms. Once request body would contain details of the room, request body would contain details of the room to be created, and the response body would contain a room identifier which was created. This would also be a staff API. Now we also want to provide a get API for the room to get details of the room. So get a room, HTTP get /v1 hotels, hotel ID, rooms. So we want the room ID. So we want to provide the room ID in the URL path, and the response would contain room details. We also want to provide an API which would list different types of rooms available in the hotel. This is the API we would call in the hotel details page for listing different types of rooms that are available in the hotel. This would be HTTP get. This is what? Room types. The response would be a list or an array of room types that are available for this particular hotel. We want to provide an API to update a room. Maybe the staff want to put this room in maintenance mode. So this would be HTTP put. We are updating a resource. The request body can contain the update parameters, and the response body can contain the actual room resource, which has all the fields. Now we want to provide an API to delete a room. This would be HTTP delete /v1 hotels, hotel ID, rooms, room ID. This would be the API to delete a room. So given all these APIs for the room resource, I think only the list room type for hotel will be used for the guest or the customer persona. Everything else will probably be used by the hotel staff or the admin persona. Now let's look into the APIs for the reservation. So for creating a reservation, we need a post API. This would be HTTP post, and the request body should contain reservation ID, it should contain start date, end date, room type, user ID, maybe total number of guests, count. So unlike other APIs, Reservation API accepts reservation ID from the client. We will see why shortly. This would be the API for creating a reservation, and the output could be a reservation ID. One, two, three, four, five, six. And it can also have a reservation status. One thing I forgot to put here is the hotel ID. So we have all the information required to make a reservation. So we have the reservation ID, which is supplied by the client, and there's the start date, end date, and room type, user ID, guest count, and the hotel ID. Okay, we need an API to look up a reservation. So v1 reservation ID. This would be HTTP GET. This would return a reservation info object, and that's pretty straightforward. And we need an API for updating the reservation. This would be, let me write down the title. This would be retrieving the reservation. Third one would be updating a reservation. This would be HTTP put, and this is also pretty straightforward. It would contain the fields that would need to be updated or that supports updating. So next one is canceling a reservation. This would be HTTP put. And the URL would look something similar to this one. So there is another option of implementing canceling reservation. We could use a HTTP delete, but then We are not actually deleting that record. We are actually just updating the status of the reservation. So I think it makes more sense to use HTTP put or HTTP patch, and to provide a cancel verb at the after the reservation identifier. So these are the APIs we would be implementing, and for the reservation, most of it would be used by user to create a reservation, to retrieve a reservation, updating and canceling a reservation. Okay, now that we have covered the API design, let's look into data model. So for data model, we have identified that there's going to be a hotel table, there is going to be a room table, there is going to be a reservation table, and there will be a table to manage users. And we also need one more table to keep track of inventory, so we will call it room inventory. We will see how this is going to be used in a while. We will also need a pricing table, and let's see. So I think this is a pretty good place to start going into details. So the easiest one would be the user one. The user would have an ID, first name, last name, all the other properties, email, phone. So nothing too interesting here. So next, let's go to the hotel table. In the hotel table, we have the hotel ID. We can have a title, we can have a description, we can have an image, and have URL as a URL to a blob store, which would have the images of the hotel, or one image of the hotel, and address. Okay, this is the hotel table. And for room, I think it would be easier to understand if I put it horizontally. ID, title, description, image, URL, address. So next, let's look at room table. It would have ID, it would belong to a hotel, there would be room type, and there would be a room number. It's redundant to mention room type, so we can just call it type. And then there would be number, there would be floor, and what else? ID, room ID, hotel ID, type, number, floor, status, whether the room is in maintenance status or active or occupied, stuff like that. Okay, now we've covered hotel, we've covered room. Let's get into reservation. So we have reservation ID. So we need start date, we need end date, we need the user who made the reservation, and the room type made for the room type, the type of the room booked for the reservation. Next, we have the reservation table. It would have reservation ID, it would have start date, end date, and user ID, and user who booked this reservation, and room type, and reservation status, created time, last updated time. We can have created time and last updated time for all of the other tables as well. So this should be good enough for the reservation table. Okay, next we have the room inventory table. We have the room ID, hotel ID. So for room inventory, we would have hotel ID, room type, and date, and total available, total reserved, and last updated. So we would have hotel ID, room type, date, total available, total reserved, and last updated. This should be sufficient. So to give an example here, let's say we have a hotel ID 1, and there are 3 types of rooms: room type 1, room type 2, room type 3. Let's say the date is for 2023 1 12 1 2023. Total available is 500, total reserved is 200, and last updated is timestamp. So for hotel ID, for hotel 1, room type 1, on this date there are a total of 500 available, 200 have been booked, last updated was at timestamp T1. This is what it would look like. And for hotel 1, room type 2, same date, let's say 100 rooms of type 2 are present, only 80 are available, last update was time. So this is what it would look like. So the advantage of this is we can easily check what the available room type, we can easily check what is the available room type for given date. Okay, that would be the database schema for that would be the data model. Okay, next we can classify these into some microservices, these entities into microservices. It's going to be a hotel service, there is going to be room service, maybe we can have a reservation service, there's going to be pricing service, and that's pretty much it. So hotel service is going to have hotel table in a separate DB, room service, and okay, then there is okay, Room service, let's say this is room DB, room table in its own DB. Reservation service can have a room inventory table and reservation table. Pricing service is going to have pricing DB, which will have pricing table. We didn't discuss what the pricing table would look like. So let's go back. Pricing table should have hotel ID, room type, date, price in cents. So for a given hotel or for a given room type on a particular day, this should be the price. So the pricing table basically gives us the pricing information for a given hotel and a room type. Okay, and we also have to decide what columns to index. So for the room inventory table, it is good to index the hotel ID and room type and the date. So we are going to be looking the inventory by hotel ID and room type for a range of dates. This is what the data model would look like. We would index specific fields depending on the queries. So for the room inventory table, we would index hotel ID, room type, and date. For the room inventory table, we would index hotel ID, room type, and date, because when we are trying to look up the inventory available, we are going to first look for the hotel and the room type within that hotel and for a specific date range. And for the reservation, we would index ID because we want to look up a reservation by the ID. Now let's look into the most important workflow, which is making a reservation. So on the left side, I'll have the client, and on the right side, I'll have the backend server. The client is going to first make an API call to establish a reservation intent. What this does is it creates a row in the reservation table and returns the reservation ID. Create reservation intent. Hotel ID. Now the server responds back with a reservation ID. The client uses this reservation ID and calls the create reservation API. And the server responds back if the reservation was successful or not. So this reservation intent workflow is very similar to what Stripe is doing with its payment intent. So here we have the server calling create payment intent API to Stripe, and Stripe returns back payment intent ID along with the client secret, which the server relays to client, and the client uses this payment intent ID and tries to complete the payment. This is the same model we are using in the create reservation intent API, where we get the reservation ID And using that reservation ID, we try to complete the reservation. So the reason we have this create reservation intent pattern is because it helps us avoid double reservation, and it also helps us avoid duplicate reservation. For example, if the user clicks on make reservation twice, it does not end up creating two duplicate reservation records. This is because on the second click, the same reservation ID is passed to the backend. Since the reservation ID is primary key, on the second request, the backend will reject that request. So that way, a customer cannot make duplicate reservations. Now let's look into the use case of how the hotel can prevent double booking. Double booking is when there are two guests trying to make the reservation on the same room at the same time. Now let's discuss about resource contention. This is one of the interesting parts of the problem for me. So here's the scenario. There is only one room available and multiple clients are trying to book that room. So how do we handle this situation? So there are different ways in which we can handle the situation. So one of the approaches for handling the situation is pessimistic locking. In pessimistic locking, we lock the rows of the database which are marked for update so that the transaction which holds the lock, only that one is allowed to make the update. All the other transactions have to wait for this transaction to release the lock so that they can update the rows next. One of the disadvantages of pessimistic locking is the lock is obtained at the time of reading, and there is a possibility of deadlocks if the order of locks obtained are arbitrary. So each transaction is waiting for the other transaction to release the locks, so that will result in a deadlock situation. Another approach of handling this situation is optimistic locking. In this approach, we introduce a column called the version column. We only let the update happen if the version number in the update is one more than the version number in the database. I asked ChatGPT to come up with the SQL commands, and this is what ChatGPT came up with. So we introduce a version number column, and then while reading the data, we also read the version number. And while updating, we set the version number to version number plus 1, but only if the version number is previously read version number. So if the update was successful, then the number of affected rows would be positive. Otherwise, we can assume that there is a versioning conflict. So those are the two main approaches for handling resource contention. So when the reads are more than the writes, it is recommended to use optimistic locking. When the writes are more than reads, when it is highly contentious environment, it is recommended to go with pessimistic locking. Now let's look into how the reservation status works throughout the workflow. When the client first makes a call for the reservation intent API to get the reservation ID, the status of the reservation would be pending. When the backend is able to allocate a room type for the reservation, the status changes from pending to payment pending. So when the status changes to payment pending, client has a limited amount of time within which he or she has to complete the payment. If the payment is successful, the status becomes confirmed. If the payment fails, the status becomes a payment rejected. Once the status is payment rejected, client again has a limited amount of time during which he or she can complete the payment successfully, or the reservation becomes rejected. Well, once the reservation is confirmed, the client can cancel the reservation. Then the status of the reservation would be cancelled. So once the reservation is cancelled, there will be a scheduled task which will attempt to refund the money. And once the refund is successful, the status changes to refunded. So I mentioned scheduled tasks a couple of times. So I wanted to give little more information about that. Let's say the reservation is payment pending. The guest usually has about 15 minutes of time before which the reservation gets rejected if the payment has not been completed or if the status has not changed. So when the status becomes payment pending, the backend would schedule a reminder message with Kafka saying, hey, remind me after 15 minutes to check the status of the reservation. If the status of the reservation is still payment pending, then it means that the client has abandoned the reservation. The system can release back the inventory for other reservations. So in a message bus like Kafka, you can schedule a topic to be published with a delay. So here we are using schedule task as a reminder to check the reservation status. Let's look into services. So we can identify these services. Hotel service to give information about the hotel. We have room service for room related operations. We have reservation service to manage reservations, and then we have pricing service to handle price related information. And this seems like a pretty good amount of services. Okay, and hotel service gets its own DB, and it would have the hotel table in it. Room service gets its own DB, and it would have the room table in it. Reservation service gets two tables. One is the room inventory, and it would get the reservation table. Pricing service has its own DB and gets the pricing table. If we were to draw this, so this would be the application layer, this would be the database layer. So in this microservice architecture, each service would get its own DB, and the hotel DB would have the hotel table, room DB would have the room table, reservation DB has room inventory table and the reservation table, and the pricing service would have pricing DB which has the pricing table. We would have a cluster manager. The cluster manager would receive heartbeats from the DB layer as well as the application service layer. We would have a load balancer. Which would send requests depending on the API to the application server. So this would be a high-level architecture diagram. So you have the pool of database servers sending heartbeats to cluster manager, and you have the application service layer which are also sending heartbeats to the cluster manager. The config store would update the load balancer, which would redirect requests to different services depending upon the APIs. The load balancer would send the appropriate requests to different application servers depending on which API is being called. And we can have a client. So now let's look at the storage replication layer. So since this application is more read heavy than write, so we have a primary database server which write requests are sent to, and those writes are replicated across a secondary database servers where read requests are sent to. So all read requests are sent to the secondary database servers, write requests is sent to the primary database server. So this is what the storage replication layer looks like. Now let's talk about the data consistency issue. So in this model, in this architecture, we have the hotel service which has the hotel DB, which has the hotel table. We have the room service which has the room DB and room table. And we have the reservation service which gets its own reservation DB. It has two tables, room inventory and reservation. Microservice architecture purists would argue that this is pretty bad. It should be divided into inventory service. The inventory service should get its own DB called the inventory service DB, which should have the inventory table. Let's talk about why microservice purists want each service to have its own DB and not let another service to access DB of a different service. One service can make a change that other service isn't aware of, and this makes it very hard to keep the data consistent. When multiple services access the same database, they become tightly coupled. So if you change the database schema, then you might potentially break multiple services. This defeats the whole purpose of microservices. If multiple services are accessing the same database, it can become a bottleneck and prevent scalability of the system. So how would we solve it if we are not allowed to club different tables into one service? So we would use the following approach where we would have another service called the inventory service, and it would have an inventory table. Now the challenge is you have to figure out how to make a transaction which spans multiple services. There are two techniques to handle transactions which spans multiple services. The first one is two-phase commit. In two-phase commit, as the name itself suggests, there are two phases. The first one is the prepare phase, the next one is the commit phase. So you have a coordinating node which asks all the participating node to prepare. And if everyone agrees, then it goes to the next phase where you commit. If there are any errors during either of those phases, you fail the transaction. The next technique is a Saga-based microservice pattern. In the Saga design pattern, you would choreograph a distributed transaction using event-based architecture. So that's how we would accomplish distributed transaction. Each of those approaches requires its own video. I'm going to cover it at a different point of time. So to keep things simple, we're going to put room inventory and reservation in the same service. So that was the system design for hotel system reservation. This was much longer than I had anticipated. If you were watching all the way till the end, drop a comment below. I'm going to follow up with some other kind of booking system so that I can practice all the stuff I learned with the hotel reservation system. If you enjoyed this video, hit that like button and subscribe for more such videos. I'll see you in my next one.